right. Hey, students. Welcome to another fun calc video with Mr. Forbes. Today we are going to be looking at our topic 3, our third lesson in our sequences and series unit. And so far we learned what a sequence was, and then we learned what a series was, infinite series and stuff like that. Today we're going to be talking more about the idea of a power series, what a power series looks like, how it's different than what the types of series we looked at in the past are. Okay. So just a little warm up here that I do not want to skip over. I actually want to do it because it's going to help us with some concepts today. Number 1, 2, and 3, I want us to just kind of refresh ourselves on how to solve inequalities with absolute values. Okay. Do you remember how this works, what absolute value means? So like another way of saying this would be like to say 2x is greater than or equal to 5 and negative 2x is greater than or equal to 5, right? The absolute value means two separate equations, the positive and the negative. So this will be x is greater than or equal to 5 for the first part. Oh, sorry, 5 halves, I divide by 2. And over here, if I divide by negative 2, do you remember what happens when you divide by negatives with inequalities? If you divide by negatives, it actually switches the sign. So you divide by negative 2, and you get negative 5 halves. Okay. Over here, this is x minus 8 is greater than or equal to 3. And negative x minus 8 is greater than or equal to 3. Okay. So for the first one, you just add 8. That's x is greater than or equal to, 11, sorry. And then for the other one, you divide by negative. And remember, dividing by negative is going to switch the sign. And then we can add 8. So x is less than or equal to 5. And lastly over here, I think we got the idea, but we'll say 3x minus 2 is less than or equal to negative 2, and negative 3x minus 2 is less than or equal to negative 2. So for the first one, we add 2 and divide, and so we get x is less than or equal to 0, actually. And for the one on the right, we divide by negative 2, so we get 3x minus 2 is less than or equal to positive 2. Add 2 and divide by 3, we get x is less than or equal to I'm an idiot. Add 2 is 4, sorry. Add 2 is 4. So that divide by 3 is 4/3. Okay. And I forgot to switch the dang sign, didn't I? I did forget to change the sign. So that's what happens when I change the sign. There you go. Sorry about that. Anywho, we refresh ourselves in solving some inequalities. Let's keep going with it. Okay. Let's talk about another examples from the yesterday's lesson with converging and diverging series. Remember that the types of series that we talked about with converging and diverging are geometric. And you can tell, like for example 4, you know it's geometric because they're all being raised to a power of n. N is only in the variable. And if n is only in the variable, that could be geometric. In fact, I can actually combine a lot of this stuff together. Like for instance, like I can actually divide both of these by 7 to the n. I can say the summation n equals 1 to infinity of 2 over 7. So how about like 2 over 7 to the n plus 4 over 7 to the n, right? I can divide each of those and bring the power out. But then remember, n equals 1, so these need to be minus 1. So remember, put minus 1 plus 1, minus 1 plus 1 for both of these. Okay? So you can have for the first one, for the summation n equals 1 to infinity. For the first one, you can have that 2 over 7 to the n minus 1. But then you're going to have multiplied by 2 over 7 to the first, which is just 2 over 7. Plus, same thing again, it's going to be 4 over 7 to the n minus 1 power times 4 over 7 to the first, which is just 4 over 7. So there it's in the correct form. So we have a summation of two separate geometric series, this one and this one, both of which the R value is equal to 2/7 and the R value is equal to 4/7. So both of these are actually going to converge because both the rates are less than 1, so this entire series does converge. So you can do two separate summations or two separate geometric series added together. So that would be like my initial value is 2/7 over 1 minus 2/7. That's ugly. Plus, my initial value is 4/7 over 1 minus my rate of 4/7. And that is going to be what the infinite sum adds up to. Very nice. I don't really want to, okay, so this is an example. This would not be geometric because even though we have n in the power right here, n is in the base right here. So it's not geometric or arithmetic or anything like that. Here we would discuss the idea of the sum. I mean, in this problem here, we can consider the top part converging and the bottom part converging. I actually want to come back to this one later because this does require a little bit different of an approach as we did on number 4. So for sake of time and sake of not overwhelming us today in this video, let's stick with the idea of geometric. Okay, let's stick with the idea of geometric because there is a way that we can approach this one. We don't really know it yet, so I don't want to try to force it yet. Okay? But we have understand how to look at a series, especially a geometric series, and identify when it converges or diverges. Sticking with the idea of converging and diverging, I want us to consider another new type of example. We learned telescoping series. I want us to take a time now and discuss harmonic series. I think this is a fun little slide to throw in here. A harmonic series is in the form with the pattern, the sequence a sub n equals 1 over n. And I think this is a very cool thing. We're going to come back to this again in our second part of this unit, but let's touch on it now. The limit as n approaches infinity of a sub n in this case does equal 0, right? I mean, that's 1 over n. That's a fraction. It's 1 over 1, 1 over 2, 1 over 3. That does eventually reach 0. So the sequence converges, therefore the series could converge. But let's talk about it. I thought this was cool. S sub n equals the summation, n equals 1 to infinity of 1 over n, right? I guess we can discuss this as an infinite sum instead of just a partial sum. But that would be like 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus dot, dot, dot. So obviously the sequence of numbers, 1/2, 1/3, 1/4, 1/5, it does go to 0. We've already discussed that. But what happens if I add these numbers up? Do you think that that is going to be an infinite sum or that the sum is going to converge to an actual number? Well, I like this because this is going to be a cool example to kind of show an idea here. I want us to, we're going to use something called a comparison test to actually show what happens with this. And a little quick mini lesson on what the comparison test is let's say we have two series here. We'll call it Series A versus Series B. There's two things that could happen. Series A could converge to a sum. Let's say the sum is 0. And let's say that Series B is always less than Series A. So I'm gonna write that out. So if Series A is always greater than Series B, like I just drew, and Series A converges. Based off the diagram here and based off of my logic here, what then must happen with Series B? If Series A is always bigger and it converges, must, think of like squeeze theorem and sandwich theorem, must Series B also converge? So that's what the comparison test says. That's how we determine if it converges. There's actually one for diverging as well. Let's consider this picture. What if series B does this and series A does this? Let's say that series B is always greater than series B. So let's write it this way. Series A is always going to be less than series B. Well, if it's known that series A is going to be a known thing. Let's say that series A, we know, diverges. And it's always less than series B. What must then be true about series B? Therefore, series B must also diverge. Okay. So we're going to keep this idea of the comparison test in mind as we show what's happening with the harmonic series. I think this is pretty interesting. So let's come up with a scenario, series A being less than series B. Let's think of it this way. Okay, I want to show you something here. Let's say that series B is the harmonic series. Let's say the series B is 1 plus 1/2 plus 1/3 plus 1/4. This is the harmonic series, right? 1/5. I'm going to keep going. I'm going to go all the way to 1/6. How about 1/7? 1/8. I'm going to go all the way to 1/9. Let's say that series A is the series that follows this form here. Okay? 1, and then how about 1/2? And then how about the fraction, if I'm comparing fractions here, how about the pattern will be that the fraction will always be less than the fraction above. Let's say this is how the pattern will work. Let's say we have like 1/2. Let's say we have 2 1/4. And then 2 1/4. Let's have 4 1/8. 1/8, 1/8, 1/8, and 1/8. Then we would have 8 1/16. And then we would have 16 1/32. That's the pattern here. So collectively, these fractions will always add up to 1/2, right? That's 2/4, which is 1/2. This is 4/8, which is 1/2. So let's say collectively we'll always have something that would simplify to 1/2 like that. Okay. Now, first of all, do we agree that series A is always less than series B? Well, yeah, because if you always compare the terms side by side, the fraction on the bottom is always going to be equal to or less than the fraction above it. And the thing we know about series A here is it's always going to simplify to 1 plus 1/2 plus 1/2 plus 1/2. And if I'm doing 1 plus 1/2 plus 1/2, that series is going to diverge, right? Series A is going to diverge because if we look at its pattern, it is always increasing. It's not getting fractionally smaller. So therefore, series B, which is the harmonic series, therefore the summation n equals 1 to infinity of 1 over n must also diverge. This is actually a pretty cool ID that we're going to use later on when we get to something called P-series. I want us to understand that the harmonic series, 1 over n, diverges. And I gave a little bit of a proof there. But I think this is a cool example to kind of counter something we haven't seen yet. The fact that a sub n, 1 over n, clearly approaches 0. So we know that the sequence approaches 0. We know that the fractions are getting fractionally smaller. But based off of a simple comparison test here, we showed that 1 over n, the sum of it is going to diverge, is going to be infinitely large, which is crazy to me. Yes, the list is getting fractionally smaller. Eventually to infinity, we're going to have it approach 0, but the sum is going to be infinite. It's a crazy concept. But something that I want us to have in the back of our minds as we move forward. Okay. We're going to jump into the big part of today. We understand converging and diverging with series now. That's kind of an idea. More specifically, we know what a geometric series is. We know this is a geometric series. And we know that a geometric series converges if and only if the absolute value of the radius is is less than 1. Okay? And if the absolute value of r is less than 1, we know that the sum is going to be equivalent to a sub 1 over 1 minus r. Okay? We would say, like, I'm going to draw out this radius. Let's say that, like, you know, we got our r value, I guess, our r value or whatever. We know that it's going to be between 1 and negative 1, right? We know that if this is going to converge, we know that this is going to converge, that my radius is going to be between 1 and negative 1. Okay, so if my radius was 1/2, it converges. If it's negative 1/2, it converges, right? So what we call that is an interval of convergence. Interval of convergence. The interval of convergence for a geometric series is the fact that it's between negative 1 and 1. Okay? If it's between negative 1 and 1, that means it's centered at 0. Okay, so we can have what's called a center of convergence as well. And we can also have something what's called a radius of convergence. Radius of convergence. It is how far out we can go from our center. In this case, that radius of convergence is r equals 1. The radius we can go out, as far as we can go out from our center here, is 1. So my range of values for r that make it converge are between negative 1 and 1. So the radius of convergence is called 1. So what if we don't have a fixed value for r? What if we don't have a fixed value of r? What if we, instead of saying r, we said, well, r depends on a variable? This is when we introduce the idea of something called a power series. It is a geometric series with variables. The sum is a polynomial. Let me show you what I mean. This is a power series. Notice that it is the same exact thing as above. It's just now I let a be a generic 1, and x is a variable, okay? The radius can be multiple r values, okay? It is a function, no longer a set value for r. If I were to expand this, okay, the technical form that we have for a power series, since the sum is going to be a polynomial, is instead of n equals 1, we actually start off at n equals 0 and go to infinity. Okay? And instead of n minus 1, we actually have it to the n power. So this is the form that you see power series in. Instead of n equals 1 and n minus 1, you're going to see it n equals 0 and n. Because it's in the form of a polynomial, and polynomials have powers of just n or just a number. If you were to expand this, this would be 1 times x to the 0 plus 1 times x to the first plus 1 times x squared, x cubed, so on and so forth. The summation is going to be what's called a polynomial, right? This looks like a polynomial. My r value, though, is a variable. It is not a fixed value. So r, my common ratio, I should say, is going to be equal to x. So keeping this in mind, remember that the infinite sum is equal to a sub 1 over 1 minus r. Only true if r is between -1 and 1. So since this is now x, this power series is going to converge to an actual like sum, an infinite sum, if and only if, okay, if and only if x is between -1 and 1. So what we're going to say is this is true, that the summation n equals 0 of to infinity of 1 times x to the n is actually equivalent to 1 over 1 minus x, which is this summation. And this is only true whenever x is between -1 and 1. It is a power series. It is a geometric series, and it is going to be equivalent to 1 over 1 minus x only if x is in between -1 and 1. So this is a huge formula that we are going to have to know. Okay? So to kind of summarize a lot of stuff that I've been saying, a power series is a series of this form right here. Okay? This form right here. N equals 0, power of n, so x to the n, to infinity. And the example we looked at before, I was looking at a coefficient of 1, but sometimes we can have a coefficient other than 1. We call c sub n, a coefficient that is dependent on n. It expands to this, c sub 0, x to the 0, c sub 1, x to the first, c sub 2, x to the second. This is the expanded form of a power series. It is a polynomial. It is a function. It is dependent on x. Let me give you an example, and I think that I would like to maybe end on this slide. I think that's my game plan here. So let me give you an example. Let's say we had the summation n equals 0 to infinity. Let's say we had some c sub n. So let's say that's 2 to the n minus 1. I'm just giving you a random example here. This is telling you a coefficient depending on what n is. And instead of a fixed r value, r is going to be a variable. We call it x, raised to the power of n. This is a power series. A power series is in the form some quantity of x raised to the power of n. Okay? This would be my c sub n. This would be my power series. Now, a note that I want to make about the power series, similar to what I said about the radius in the last problem, or the rate in the last problem, is that this power series, we're going to say is centered at x equals 0. X equals 0 is the center. The interval of convergence is the same for that of a geometric series. Instead of r being between -1 and 1, we're going to say that the interval of convergence is between -1 and 1, but with an x. So whenever my x value is, say, 1/2, if I plug 1/2 in for x, this would be a geometric series that converges. Okay? What the expanded form looks like, if I plug 1 into this, this would be 2 to the 1 minus 1 power. Or I'm sorry, 0 is the first point. If I plug 0 into this, this would be 2 to the 0 minus 1 power, or 2 to the negative first, x to the 0. Plus, that would be then 2 to the 0, x to the first, plus 2 to the first, x to the second, plus 2 squared, x to the third, plus, and the pattern continues. Okay? And what this would simplify down to, if I had an infinite series, would be the first term would actually be just actually 1/2, plus 2 to the 0 is 1 times x to the first is x, plus 2 times x squared, plus 4 times x cubed, and so on. That is a expanded form of a power series. It is just a polynomial with increasing powers. Okay? So just to summarize, what we should know from this video now is what the form of a power series looks like, what an interval of convergence is, the fact that the radius of this interval of convergence is 1, and that's going to be true always, well, almost always for power series. Okay? And tomorrow we're going to look at, well, when we talk about the rest of this lesson together, we're going to talk about series of power series centered at something other than 0. And we're going to look at an example of how to represent functions as power series. So we should be able to finish right along here. So good job. I'll clarify any questions we have on this material together. But the big thing to take away from today is what the form of a power series looks like. All right. Good job, guys.